NASA's Jet Propulsion Laboratory presents the Von Kármán Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. May the 4th be with you. Wow. I got a live long and prosper sign right there in the back. Thank you for joining us here at JPL, and thank you for joining us at home for the Von Kármán Lecture Series. Now let's get to it. The Cassini mission has revolutionized our understanding of Saturn, from its complex rings or magnetic environment to its menagerie of moons. Icy jets shoot from the tiny moon Enceladus. Liquid ethane and methane dominate Titan's hydrocarbon lakes and seas, and Hyperion has a static charge. We look forward to the puzzles Cassini will solve as it goes out in a blaze of glory. Tonight, our guests will reveal some of the recent science discoveries and share the excitement and challenges expected during Cassini's final orbits. Now, Dr. Earl Mays is the Cassini program manager, a veteran of 32 years at JPL. He began his career working on the navigation and engineering teams of the Galileo mission to Jupiter. After Galileo's final Earth flyby, he transferred to Cassini as a spacecraft operations manager and then deputy program manager. He left the project for 8 years to hold management positions in guidance, navigation, and control and avionics, then returned to Cassini as program manager in January of 2013. Now, Dr. Linda Spilker is the Cassini project scientist and co-investigator on the Cassini Composite Infrared Spectrometer team and has worked on Cassini since 1988. Since joining JPL almost 40 years ago, her first and only job out of college, by the way, she has worked on the Voyager project, the Cassini project, and conducted independent research on the origin and evolution of planetary ring systems, while also supporting proposals and concept studies for new missions to the outer planets. She enjoys yoga and hiking, especially through her favorite park, Yosemite, and is married with 3 daughters and 5 grandchildren. Right? Ladies and gentlemen, going out in a blaze of glory.
A lone explorer. On a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a 1 million-mile trek to Saturn. We have cleared the tower. Bridge program is in. Roll program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Cassini is on a collision course with Saturn. In the next 4 months, every week, we'll be coming a little bit closer and a little further away until finally on September 15th, very early in the morning here, about 3 a.m., it will enter the atmosphere, going at about 75,000 miles per hour. At that speed, the spacecraft won't last long. It will quickly lose control, begin to melt, and eventually vaporize into the very planet that it went to explore some 20 years ago today, 20 years ago. So you might wonder, that's such a hot idea. I mean, you've got a perfect spacecraft. You've been rewriting the history books and the science text ever since you got there, and in fact, even beforehand. Well, for the next maybe 45 minutes or so, Linda and I are going to try to at least explain why we not only think this is a good idea, but a great idea. So quickly to the pad and beyond, as the movie showed you. We launched in 1997, absolutely flawless, a beautiful launch from the Cape on a Titan 4B. And 6.5 years later, after a very circuitous tour of the middle and outer solar system, we finally arrived at Saturn on June 30th, 2004, and had an absolutely flawless orbit insertion. For the next 13 years, we were doing pretty much this. Now, don't be alarmed. This is something we call the ball of yarn. This is the entire mission, all 293 orbits, some of which we haven't finished yet, beginning with SOI and continuing on. What happens here is that for the last 12 years, we've been using Cassini's rocket fuel and Saturn's largest satellite, moon, Titan, which is a mission designer's dream, to move us all through the Saturn system. So we've been able to, I probably can't see it in here, but right in the middle of all this, there is Saturn. So we've been able to actually go to these very highly inclined orbits, so we come down over the tops and look at the rings and look at the poles, at these very long looping orbits out to examine the magnetosphere way outside of the influence of Saturn itself. And then, of course, these in-tight orbits to investigate Enceladus and the icy moons. So for the last 12 years, up until last November, this is pretty much what we've been up to. A fascinating tour and an amazing set of discoveries. We'll get to a little bit of those later, and I think Linda will show you even more as we move on. But I want to jump back to the reason that I started with this whole premise of why are you doing this? Well, Saturn's got some ocean worlds. These are pictures essentially Voyager-class pictures of the moon Enceladus and Titan, both mysterious in their own ways. Titan enshrouded by this veil of orange haze that we couldn't penetrate, and Enceladus exceptionally bright, but quite small, 300 miles across, so essentially a bright snowball. Well, by the time we were done, or Cassini was done, I should say, I'll take some credit, but not all of it by any stretch. Enceladus had turned out to not only be differentiated, but to have plumes, a warm global saltwater ocean, and hydrothermal activity. And if you notice that we just had a press release not too long ago that there is atomic hydrogen out in these plumes, all the ingredients for life on this little tiny moon. Absolutely earth-shaking discovery. Sorry, it's a bad pun. But really, just everybody was floored. We had no idea this was going to happen. And then on top of that, Titan was revealed to have lakes, a hydrologic cycle. Of course, it's not water, it's methane and ethane. Rain, clouds, rivers, estuaries, and it too has a subsurface ocean. So we've got two places that really just need to be kept as pristine as we possibly can. And I got to say that there's something about Cassini that, while it was a perfect spacecraft, it's not all that perfect. Well, we're out of gas. There's very little fuel left. And what happens, even though we were able to use Titan, as I showed in the other slide, quite effectively to move around in the Saturn system, we still need the propellant to keep the spacecraft oriented and on track. So without propellant, eventually it would be running out of control. And as we've come to discover with Titan and Enceladus, an uncontrolled spacecraft encountering these moons could eventually result in an inadvertent impact, which would cause us all sorts of embarrassment and some concern for future exploration. So we had to do something about it, and what we decided to do was what we call the grand finale. So let me back up a little bit and talk about these are the final 6 years of the mission without the F-ring orbits. When we were discussing various options for the eventual, there's no euphemistic way to put this, the eventual disposal of Cassini, a lot of different options became available. But the one that just absolutely was most compelling was to actually stay inside the Saturn system, investigate as much as we can, use all the gas we possibly could, and then put it into Saturn. So this is what we've settled on, and as I think I'm going to try to continue to lead you towards the fact that this is an absolutely phenomenal end to a great mission. So this, again, is the ball of yarn, if you will, for the last 6 years. This began back in 2010. And what we've been doing, as you can see it even better here, every one of these little nodes, these little knots, is a crossing of Titan. And Titan has been moving us all through the system as it did for the previous 6 years. And what happens next, though, is really fun. We find a Titan orbit, and the mission designers have just been absolutely brilliant with this, found a Titan that took us into what we call the ring grazing orbits. These orbits actually are in tight and are grazing tantalizingly close to the F-ring right here. 20 of these, and we just finished them up a little while ago. Absolutely phenomenal set of orbits that have provided entirely new insights into the rings and some of the ring moons. Better than we've ever been since SOI, and closer we've ever been since the orbit insertion. We've never been in this close again before. So, well, what do we do next? There's one more Titan flyby coming. This is the final of the F-ring orbits. Now, what I want you to look for is a Titan flyby that's going to come sneaking around here and give us one last little push. This is the last orbit, boom, around the F-rings. Now watch it, here it comes. Here comes Titan. Watch what's going to happen to our orbit. It's going to suck just a little tiny bit of energy from Cassini. Just enough to put it between the rings and the planet. First of our ring plane orbits. And that's number one. We just did number two actually Tuesday, and we've got 20 more to go. Those are the grand finale orbits. It's an absolute pinnacle of astrodynamics and science achievement. So very exciting. Let me just give you another quick glimpse of these. This is going to be all 22 of them, so hang on for a while. But what I wanted to show you is that Titan has been our friend and moving us all around for the last 13 years. And we're calling this final Titan flyby the goodbye kiss. It is coming in right now, and we're going to slow down just a little bit after 22 of these. Titan's going to come swirling in from the side. There it goes right there. And what that's going to do is it's going to steal just a little bit more energy. Just enough so that Cassini is going to go into the planet itself. That's the 75,000 mile per hour hit a brick wall kind of encounter that the spacecraft will not survive. And again, the point is that we absolutely must put the spacecraft into a position where it can inadvertently contact either Enceladus or Titan or any of the other icy satellites, which we believe are also potential for further exploration. So let's just see how we do here. All right, so we've got the orbits, right? We've got a challenging new set of orbits, a whole new regime, but we've got an old spacecraft. So the first question we've got to ask is, can we teach this spacecraft new tricks? It's going to go into a new region, it's going to do different things, and of course, with any kind of learning experience, there are constraints. We've got folks on the science side that say, look over here, look over here. The Saturn's really cool. On the other side, they're looking at the rings. No, look over here. And then you've got the engineers. I probably consider myself one that's saying, you got to be bold. You got to do, dare mighty things. Well, wait a minute. We ought to be careful. It's dangerous over there, and it's dangerous over there. So what's going to happen? The spacecraft, of course, is, I'll do what you tell me. Just got to tell me to give me the right orders. So it's a bit of confusion. Let me just try to answer the question that we've tried to deal with between the bold, the mighty things, and be careful not to do anything too crazy. And that is the gap. There is a very narrow gap. It's 1 billion miles away, so 1,200 mile gap is kind of narrow. And it's been a big deal for us to worry about this. And so let me just give you a couple of animations that one of our mission design engineers put together, which really, I think, give you an idea of what's going on here. These are the 22 orbits, and this is the final orbit. And here is actually a pretty nice and pretty accurate rendition of Saturn and its rings, an artistic representation. Here is what it looks like with a high contrast photo. So you can see we are flirting very close, the atmosphere on one side and the dust on the other. So it's not quite as easy a shot as it first appears. If you now take a look at this a little bit closer up, you get a bit better view of our ring plane crossings and our periapses, or minimum altitudes, which are all in the southern hemisphere of Saturn. One last look, and you can kind of look down the orbital path, and you can get a sense of just how close these are to the Saturn itself, and how much Titan, who's still out there pushing us around, is moving these various orbits around. And then finally, you see our final orbit over in the end. It doesn't show up well here, but it's there. So what do you do with that? Well, first thing we engineers do is we put that into an XY chart, right? What else would you do? It's data. And so here are our minimum altitudes, and here are our XY plane crossings. But then, of course, what you want to do is put your boundaries on. And what we've done is we've more or less decided that the extensible edge of the D-ring is about 6,400 kilometers from the center of Saturn. And we picked some orbits that we thought were pretty cool. They've got a lot of moving around in here. They go down into the atmosphere, and then finally down here you'll notice our final orbit. But they do some things up here that are a little bit alarming. They take us up into the dust. So we had to figure out what we're going to do about that. There's a high contrast photo again of the dust, and there's that boundary, and there's the range that we're in. So we had to come up with some sort of scheme as to how to deal with the dust. We modeled it completely. We feel like it's safe in all the models that they've that the ring scientists, and we've got the best ring scientists in the world, as you could imagine, on the project. So we really didn't have a lot of worry, but you never know. We've never been there before, so we had to see what was going on. And so there's the region we were trying to avoid. And what we decided to do for these up here was shield them. Now, if you notice the images of Cassini, it's got a large, well, it's right over there. There's a very large saucer-shaped antenna on the front. Pretty solid piece of material, and almost all the instruments are behind it. So if we go into the dust with that antenna pointing into the dust, everybody's pretty fine, except, of course, for that long magnetometer boom, which is exposed. But there's not a thing we can do about that. So for these crossings, we decided that we would protect the spacecraft by the shielding. Furthermore, since we really didn't know where we were going, or, well, we knew where we were going, we just didn't know what was in there, we decided to put a shield on our first flyby as well. We've now completed that flyby and completed, I'm calling them flybys, they're ring plane crossings. Completed that one, and I got happy to say the spacecraft's come out just fine. So let me show you just a little bit of what that looked like. This is our first crossing, right? And you're gonna watch the spacecraft reorient itself as it goes through the dust and point the high-gain antenna right into what we call the ram direction. That is the direction of oncoming dust. And of course, being as opportunistic as we can, the minute we're through the dust, we turn the spacecraft back around and start imaging the planet again. So just for a few minutes on either side of the ring plane crossing, we use the spacecraft antenna as a shield for the rest of the instruments. That went perfectly fine. Now, you want to see some drama. It's not this, it's me trying to make it work. I'm going to see if we can do this. This is, well, let me explain it a little bit first because I'm going to mess it up. This is the, what we call the radioplasma wave spectral analysis of the ring plane crossing. And what happens is, as dust strikes the spacecraft, it creates a plasma. It's an ionized gas, and our antenna can pick them up. And so the more dust you run into, the more energetic, more plasma you get, and you get exactly what you'd think you see. This is time, and this is, in a certain sense, a measure of the plasma or energy. And so you see a very high peak right here at the ring plane crossing. This happened during one of our F-ring grazing orbits, and it was just classic, ring grazing material. So what I want to do, if I can get this, if I can find my mouse here. Oh, there it is. So this is the sound file of what we consider a normal dust crossing. Right, you can see the little line going through. So you can see hear both some of the low-level particles, the kind of the smaller particles. Every now and then you hear a larger bip of a more energetic or a larger particle striking the antenna. That was with the high-gain antenna shielding us. So here's what we saw during our first proximal orbit passage. After all these dire concerns about the dust, I'm not going to spend a whole lot of time trying to find this audio file that doesn't sound like anything, because this was absolutely silent. We had the noise turned up so we could just find something. Turns out that all of this drama about the D-ring and all of that dust in between that gap was actually just a big empty. We don't quite understand it. Well, I should say the ring scientists are still befuddled by it. There shouldn't be that little dust there, but something's cleaned it all out. So I think, as one of our mission design folks quipped, Saturn has swept the doorstep free for us, like a good host. So indeed, so far, we've had perfect ring plane crossings, and the drama about any dust issues or things like that seem to be for naught. Okay, so we've just talked a little bit about how to avoid the dangers using the high gain antenna and things like that. Now what about, look over here, look over there. We've had 22 orbits, sounds like a lot, but we've got 11 functioning instruments and 5 other investigations that try to share instruments, and there's a huge amount of conflict between this. And so it was very heartening. We started working on this years ago, that the instruments figured out new ways to use and cooperate on these 22 orbits. For example, we have the gravity folks that when we're doing gravity science, they want to have the antenna pointing to the Earth. And they want to have it rock solid because they're trying to measure incredibly subtle variations in the signal as it passes between the rings and Saturn. The magnetometer folks want to roll because they want to spin that big boom through as much space as they possibly can in order to get the best magnetic field data. Well, they found a way to spin on an axis that keeps the radio bore sight directly pointed at Earth. And so they get to spin, and gravity science gets the benefit of their, again, a beautiful collaboration. We figured out a way to repurpose the INEMs to become an atmospheric probe. The spacecraft can now use the data that's on board, normally stored on board, and shoot it down immediately. So as we're burrowing into the atmosphere, we're sampling data to the very last instant. There are bunches of examples of that. So let me just go to this last slide. This, again, is all of the periapsis passages all along here. And as you can see, they are spread around, but we really had a tremendous amount of contention. And what happened was that almost all of them shared. Instruments are collaborating on all those circled orbits. There's collaboration between the radio science and magnetometer, between dust and mass spectrometers, it goes on and on. So we've maximized every piece of science that we can get out of these orbits. And with that, the amount of time I've wasted, here is the Cassini poised for its first flyby. And I'm going to segue into the grand finale objectives, some of the unique science, and put Linda Spilker on. Thank you for your patience.
Okay, well, I'm Linda Spilker, and I'm the Cassini project scientist, and I have a really cool job. I get to coordinate amongst 300 scientists spread around the world to get the best science possible for the Cassini mission. And I've been lucky enough to be with this mission for a long time. It's been almost 30 years that I've worked on Cassini. In fact, my oldest daughter, Jennifer, just started kindergarten when I started working on Cassini. And now she's married, and she has a daughter of her own. And what's so amazing is how quickly those 30 years have flown by. And in fact, here's sort of, basically I've been on the Cassini mission for one Saturn orbit. It takes Saturn about 30 years to go around the sun a single time. And so what's shown here are the mission phases as a function of Saturn orbit. So you can see we, as Earl said, we arrived in 2004, had a 4-year prime mission, 2-year equinox mission. We're now in our 7-year solstice mission, and we're at the very tail end. As Earl showed you, we had just finished our ring grazing orbits, and we're now 2 dives into the grand finale. So what I'm going to do is I'm going to step back and show you some amazing pictures and science results from those ring grazing orbits. We basically pulled Cassini's orbit in very close to Saturn's F ring, which is nestled right against the main rings, giving us a chance to get incredible pictures. In fact, if you look in the blue region, we could get incredible pictures of tiny little moons that orbit in the gaps in the rings, next to the rings, and the best pictures ever of the rings themselves. So here you can see a couple of gaps, the wider gap over on the left, that's the Encke gap, and inside of the Encke gap is the moon Pan. Now Pan was actually discovered in the Voyager data, but not until 10 years after the Voyager flyby, where Mark Showalter put together the images and figured out there was a moon and where to look for it. The next gap out includes a little tiny moon named Daphnis. Cassini discovered Daphnis in 2005. And finally out hugging the edge of the A ring is Atlas. And Atlas was discovered in the Voyager data as well. So to really see these little tiny moons, it takes a spacecraft. So let's take a look at those. First, let's look at Pan. Here's a movie that we took with the Cassini spacecraft. These are raw images. You can see cosmic ray hits and so on. But here, I'll back it up and show it again. We went zooming by this tiny moon. And you can see it looks unusual. It's not It doesn't look like a potato. It doesn't look like a round moon. In fact, here's a couple of views of Pan. Pan's about 20 miles across at its equator. It's nestled in a 200-mile-wide Encke gap. And you can see it also has this very interesting equatorial ridge or skirt of particles. And what it does is it's accumulating particles from the edges of the Encke gap, and they go around the equator of the moon. And sometimes those particles actually slide out. It's hard to see here, but there's actually you can see a landslide of particles in a couple of places where they slide down onto the main central frozen moon itself. You can see tiny little craters, some ridges inside of along this ridge here. So very interesting and unique. In fact, one of the Cassini scientists said, that reminds me of cheese dumplings. So you can see the edges on these cheese dumplings, so a very, very unusual shape. Well, it's moving on to Daphnis. Daphnis is much smaller. Daphnis is only 6 miles across, and it's holding open a 25-mile wide gap. Turns out that these moons are big enough they literally shove aside the ring particles and create a gap that goes all the way around Saturn's rings. So if you're a big guy, you get in the rings and you say, move out of my way, and you can create a gap. Daphnis also, as well as Pan, creates waves along the edge of the gap. Here's another view of those waves. You can see actually a tiny tendril of ring particles that Daphnis has pulled out. And just like the waves in an ocean, you can see this wave going along and slowly damping out, and the particles actually shearing apart. So just very beautiful, very close-up views, incredible detail in the rings themselves as well. Let me go the right direction. And this is a movie of Atlas. Now, Atlas is the moon. It is about 26 kilometers across and only 11 miles north to south. And so you can see here's a close-up view of Atlas. It's not washed out like this on my screen, but it's much smoother, very few craters. There's a big icy particle in the center. It turns out these moons can't accumulate ring particles forever. They get out to a certain size, and then their gravity gets balanced by Saturn's gravity. So any ring particles that try and stick get pulled away by Saturn's gravity. So Atlas has grown pretty much to the biggest size it can around its equator. And here are the 3 moons shown to scale. There's a scale bar of 6 miles. So you can see Daphnis truly is tiny. And it really took Cassini's very stable, good cameras to be able to find tiny Daphnis. Now here's one of my favorite pictures. This is going all the way back to 2009. The sun was edge on to the rings. And at that point in time, basically the sun's edge on, at that point in time, anything that sticks above or below the rings will cast a shadow. And that's called equinox. And so you can see shadows, many, many, many shadows, cast by objects probably 1/3 to 1/2 mile in size, probably accumulations of particles, maybe bigger particles as well. But we've never been able to really resolve or see one of those particles up until very recently. This is the same view now turned sideways. Here's the edge of the B ring, and you see all of this speckling, and those are individual clumps now that we can resolve at the edge of the B ring. Incredibly detailed structure. We were thinking as we got to higher resolution, the ringlets would just appear to get wider and we'd see more structure, but instead we see more and more ringlets. Every time we get closer, the ringlet that's there divides into more, and it's just an incredible detailed structure. Now I got this picture from Matt Tiscarino, and he tried something very clever. He realized if you could fold the picture over essentially along a line that's perpendicular to the rings and subtract the 2 halves, anything that's different as you go along the azimuth in this direction along the rings would show up as additional speckling. So he did just that, and you can see, of course, the edge of the B ring has lots of these little speckles. It's very different as you go from one place to another, slowly dies away, but then there's a couple of other places that have a lot of speckles in them too. And it's very sort of hidden away in that other image, but you can see them now, and so now we have to explain why can you get clumping so far away from the edge of the B ring. So lots of new science and just a handful of pictures that have come back in the ring grazing orbits. And then, of course, these very interesting objects called propellers. If you're a tiny moon, you're not big enough to make a gap. What these propeller objects are trying to do, there's an object in the middle here trying to open up a gap. It gets a partial gap. Those are the 2 arms of the propellers. And we had a lot of fun. We named the propellers after aviators. So you'll find in Earhart, in this case it's Santos Dumont. And you're seeing a view on the lit and unlit side. This is about a mile across in width here. The object is probably a 1/4 mile or so in size. And so these objects are like the seeds that you would have in a disk from which the solar system formed. So Saturn's rings are really a laboratory where we can watch dust interacting, how you could grow larger objects, planetesimals, that could go on to form a solar system. So studying the rings gives us ideas about how our solar system formed and how you could get solar systems around other stars. So very exciting to look at as well. And this is a very interesting picture. This dot here, it isn't a star, it's not a cosmic ray hit, that's the Earth. That we turned the Cassini cameras on April 12th to take our last picture of Earth in between the edge of the A ring and Saturn's F ring. And if you look very carefully and blow it up, there's the moon. So you're actually seeing the Earth and the moon. And if you were on the Earth, this was over the middle of the Atlantic Ocean when we snapped this picture. So it's a very special time. We have to use Saturn to cover up the sun so we can turn our delicate cameras close enough to the sun, but the sun's covered, to take this very unique image. So this is our farewell picture, our last picture of the Earth. Now, Earl showed this. This is the historic first passage. This is the start now of the grand finale, going in between the rings and the planet, flying in a place that no spacecraft has ever flown before. And that's very exciting because every time you go someplace new, you're going to make new discoveries. And that's exactly what Cassini did. If you're riding along with the Cassini spacecraft, here's what it might feel like as you're peering over the edge of the antenna to dive in between the rings and the planet. You're going at 76,000 miles an hour, and it only takes you an hour to go from over one pole of Saturn to over another. And then you come back out the other side, and you do this every 6.5 days. So you're coming in very quickly. You can see the background of the Milky Way. You come out the other side. You can see the sun here as you go on out. So just a very exciting time in the mission. So what did we see on that first dive? We actually, on this first dive, we used the high gain antenna to protect the spacecraft, but we rotated to point the cameras at Saturn. We started at Saturn's North Pole, and we just kept taking pictures every 17 seconds from the North Pole down toward the equator. And here you can see views of some of those. Here's the giant vortex, hurricane-like, right at the North Pole. Some of these clouds that are better resolved than we've seen before. Here's the edge of the giant hexagon, a 6-sided jet stream that's 2 Earth diameters across, centered on the North Pole, then down to some of the other images. So I'm going to show you some of the other additional ways to look at this data. One is here is what the spacecraft was doing as we were taking those pictures and looking at Saturn. So you can see that we're going down. You can watch those little picture frames getting smaller and smaller and smaller as we go down it. You'll see shortly a turn as we point the high gain antenna down into the direction of particles, but we're still taking pictures. We're still taking science data all of the way through. Here's another view. I like this view because the red dot is showing you where you are on Saturn, and here's those pictures as if you're gazing out of a tiny window looking down on the planet. So you can see all of the detailed structure. These are all up on our webpage if you want to go and take a look at those. There's the turn for the high gain antenna, and we'll stop here shortly. And then just to, this is just really an up-close view of those first pictures that came back. And we were gathered on Wednesday night. It was just, a little over a week ago. We were gathered to wait for the first, dive to come through. It was actually on April 26th, which was my birthday. And what a great birthday present to make it through successfully through the ring. So that was really a good day. And as we watched these pictures come back, lots of us were here until about 2 in the morning or so. One of the leading Saturn scientists, Andy Ingersoll, said, "I've never seen anything like it in my life. I don't know what it is." And that's half the fun. You go there and you're not sure what you're going to find. Now this is the second dive. What you're seeing here is a movie. It's showing the Cassini spacecraft along this orbit. It'll cycle a few times. Here, let me back it up. It'll cycle again. Here's Cassini. This is the magnetic field lines. The strength is color-coded. And we're turning the spacecraft. This is showing you an hour. And we're turning Cassini the whole way through that time. And that's to calibrate the magnetometer and get back data. And we were clever enough to have just the right instant in that turn to have the cosmic dust analyzer looking in the direction of the ring plane. Our hope was it would sample the ring particles and give us composition. But as Earl said, it's pretty empty, and so there wasn't a lot to see for that time. Here's some pictures that came back. I just went to the web and pulled off a few of them. This is a star, and this is what happens when a star gets overexposed in the cameras and is extra bright. Here's the F ring, and then here's part of Saturn's A ring. Another one of the F ring, it's very kinky and clumpy, very unusual. We took a very long movie as we flew through on this particular pass of Saturn's F ring. Well, let me give you some of the highlights of the science that we're going to be doing in the remaining 20 dives between Saturn and the rings. Well, of course, it involves the planet itself and the rings. If we start with the rings, one of the things that Cassini can do is for the very first time measure the mass of the rings. Right now, that mass is uncertain to 100%. We don't know what it is. But by diving in between Saturn and the rings, we get just the mass of Saturn by itself. Earlier in the mission, we have the mass of Saturn plus the rings. Subtract the two, you get the mass of the rings. Now, if the rings are more massive than we expect, then they could have perhaps formed at the same time as Saturn. They could have been massive enough to have survived the micrometeoroid bombardment and erosion that took place to be there till today. Less massive, they must be young. Perhaps only 100 million years old, a small fraction of the age of the solar system, perhaps forming from a comet or a moon that got too close. Saturn's gravity ripped it apart. Those pieces went on to form the ring. We still hope to get the composition of the rings. We just have to get a ring particle into our cosmic dust analyzer. Then for the planet itself and also for the rings, we'll get some of the best pictures ever of the hexagon, of the storms at the poles. You've seen one swath. We're going to do that again, perhaps get some color, exquisite pictures of those inner rings. Who knows what we'll find when we take a closer look. Then, of course, on the last 5 orbits, we're literally dipping our toe into Saturn's atmosphere, and our ion and neutral mass spectrometer will be tasting the composition. It's mostly hydrogen, but there are other things there as well. And so for the first time, directly sampling the upper atmosphere of the planet. There's a radiation belt there. We know from solar insertion there's a very weak radiation belt, not nearly as strong as the main belt outside of the rings, so we hope to characterize the radiation belt and the plasma environment in that gap between the planet and the rings. Then, of course, we're going to study the magnetic field, these blue lines coming out from Saturn in exquisite detail. One of the things we still don't know is the length of a Saturn day. How fast does Saturn rotate on its interior? Because when you look at the outside, all you see are clouds. And different latitudes rotate at different rates, and so we want to know what's the rate of rotation. It's around 10 hours, maybe 10 hours, 20 minutes. What is it? And we're hoping if the magnetometer data shows us the magnetic field is tilted just a little bit, it'll swivel around like a giant lighthouse, giving us the length of a day. We also want to know, where does the magnetic field originate? The atmosphere is gas at the top. That hydrogen compresses to be a molecular hydrogen liquid, compresses some more until it becomes metallic. It's metallic in a phase where currents can flow and generate a magnetic field. We think it's about half a Saturn radius in, about 1 million atmospheres of pressure. That's what our models tell us. So we'll get a chance to find out, see what the inside of the planet is like. We'll study the aurora in more detail. Particles come in along the field lines, crash into that area, create aurora, and they're pink and purple, because it's hydrogen that's glowing and emitting in the aurora on Saturn. And then finally, looking at the interior itself, with our gravity measurements, the size of a rocky core, is it 1 Earth in size, 2 Earths in size, what's the boundary like? How deep do the winds go? Is it 300 miles, 3,000 miles? When do you start to feel the winds peter out? And we think with the gravity measurement irregularities, we'll be able to pin down the location of those winds. Then, of course, on that final orbit, we go into Saturn. And that's going to be a really, I think, a tough day to say goodbye to this spacecraft that's been around for so long. And when you think about it, with Cassini's final heartbeat, that's humankind's last intimate personal connection with Saturn. That connection will be cut. And we'll no longer be able to see those little tiny moons that I showed you pictures of tonight, or Saturn's F ring, because you see, they'll be lost in the glare of Saturn and its rings, except for once every 15 years when the rings are edge-on to the sun and the rings go dark. Then we'll get a chance to catch a glimpse of these little tiny worlds that Cassini revealed. But we have 20 more dives through that gap before we get to the end. So we have a lot more new, exciting, incredible science ahead. So join us, check our webpage, look at the great pictures coming down, and enjoy these final heady days of Cassini's grand finale. Thank you very much. Earl and I'd be happy to take questions. If you wouldn't mind, please using the microphone in the back, and that way everyone will be able to hear you. So if you can go in the back and use the microphone, that would be great. Go ahead.
Yeah, in the early 70s, I, along with two now retired colleagues, developed the model for the gravitational attraction of a disk, which Voyager navigators said was rather critical to Voyager actually to go to Uranus instead of some random place. I'm kind of surprised that partial derivatives of your trajectory with respect to the mass of the rings using that model don't give you better information than 100% of an error bar.
Well, sort of the question is, you know, you need to know the mass of the rings to have sent Voyager on to Uranus, so why don't we know them better from our navigation data? Well, if you look at it, the mass of the rings compared to the mass of Saturn is absolutely tiny. So in a certain sense, you know, the rings are kind of in the noise because Saturn is so massive. So even after all, you know, we have it down much more precisely than we had for Voyager, but it's still a large error bar.
Another question also. I assume that when the line of sight between the Earth and the spacecraft passes through Saturn, that you are getting information of the atmospheric composition using microwave spectrometry.
Right, right. That's a very good point. There are other kinds of things we'll be doing with the spacecraft. We can actually use the radio signal occulted by Saturn to get occultations of the atmosphere, of the rings themselves, and do a lot of other science focused on Saturn as well. We'll actually get radar on the rings for the first time too. And we've been doing that throughout the mission, using the radio beam or stars to get occultations of the planet and of the rings.
Thanks, Tom.
Hi, I'm curious if you could talk at all about how you made the determination that it was going to be safe to pass between the rings and Saturn. I know you talked a little bit about the ring scientists did a lot of work in determining that the dust environment would be low enough Cassini could survive, but since it had never been explored before, how could you make that with enough confidence to say, yeah, we'll risk it and let's go?
Well, we had a model, and what we did is, Earl showed it earlier, we took a picture of the innermost part of the rings with Saturn's shadow going across it. And we knew the shadow was very black and very dark. We looked at our image, we stretched it to see where that boundary went relative to the shadow. But in the images, all you see are the tiny dust particles. So we felt we understood the dust very well. But the bigger particles, if there aren't very many of them, you don't see them. So we were just sort of assuming, okay, let's assume it's sort of like when we go through the E ring or the G ring, just little particles and extrapolate in. Our extrapolations told us we should have less dust than we saw in the E ring or the ring grazing orbits, but there was nothing in the model to say there'd be no dust. So, but part of it, the bigger particles, that was a risk though worth taking.
Thank you.
Thanks for the great talk. I had a question for each of you. First question, on the animation depicting Cassini's first travel through the ring plane, it appeared that the mag boom was rotated towards the D ring. Is that accurate? And would there be any difference between particulate risk on either orientation?
No. When you're pointing into the RAM, the mag boom is equally exposed, and so that was a preferential attitude for the magnetometer itself. So.
Yeah, if you look at the Cassini model over here, you can see the mag boom, that big golden boom. It doesn't matter how you point the space, well, for the high gain antenna protecting the rest of the spacecraft, the mag boom's hanging out there. Yeah.
Second question, On the equinox slide that you had, there's a lot of vertical perturbations, and it looked like they were all 90 degrees from ring plane. What are the mechanics behind that?
Well, in that image I showed from equinox, the sun direction was shining from above, shining down. And so that small piece of the rings that you saw, it made them look like, you know, all the shadows were going out in a single direction. Why the clumps happen to be at the edge of the B ring, there's a resonance keeping the edge from spreading, and maybe the clumping, there's a lot of clumping that happens in that region as the particles, like a crowded freeway, they're trying to merge over and they can't, so they're starting to clump together.
But the main question was on the vertical extension of that. If a moon is traveling by and caused a perturbation, wouldn't that be bent or inclined as opposed to straight out of ring plane?
Oh, everything pretty much at Saturn. It's a very interesting question. The rings on average are only about 10 feet thick, and Saturn's oblateness tends to keep everything very, very coplanar. So they don't tend to have inclined orbits. There are other places in the rings with inclined orbits, bending waves, et cetera, but not generally across the rings, not at the edge of the B ring.
Thank you.
Yeah.
Yes, all the orbits of the spacecraft that I saw here looked extremely elliptical. Is there a way that you could have obtained a circular orbit? And if so, could you have continued the mission by attaining a circular orbit within the ring gap, considering now that you know that there's very few particles in there, and then you wouldn't have run into much resistance, and if it eventually decayed its orbit like a satellite around Earth, it would just crash into the planet anyway, and it wouldn't present any hazard to the moons.
Well, I think a circular orbit's always an option, but it's not a very scientifically interesting one. One of the things we really did have to, if you're going to use Titan as a circularizer, and that's really the only way we could have done it, you're going to have to come back to Titan. There's no way to avoid it. So you're essentially going to be in some sort of Titan-like orbit. And if you're going to be doing that, you're eventually going to have to deal with the fact that you're out of propellant and in an orbit you don't want to be in with Titan messing with you. There were some other options for very large elliptical orbits that were also stable, but the scientific value of those relative to these grand finale orbits was so marginal that they were dismissed almost immediately.
Right. In fact, the scientists kind of looked down this table of options of what we could do, and they saw the grand finale, and they said, that's it. End of discussion. We don't need to talk about it anymore. So they like that.
Yeah, granted that because of the way the mission proceeded, it's no longer an option. But if you'd known when you started the mission what you know now, would it have been possible to end the mission with a spacecraft in a circular orbit within the ring gap?
Oh, within the ring gap?
Yeah.
I don't think so.
And why
Simply because there's, where are you going? You're going to have to find something to circularize you at both the periapsis and at the apoapsis, and I'm not quite sure. I'm not going to stick my neck out on that, though. Again, if you're using Titan, and that's really the only thing we've got, you're going to have to end up coming back out to Titan again.
So there's no way, you couldn't carry enough fuel to do that. You'd have
Well,
to
that would be the thing. And no, I don't think, well, I'll let Linda speak to the scientific merits of carrying that much propellant and then using it to go inside the rings and stay there. But you could. I mean, conceivably, you could take enough propellant to go in and actually, once you've got periapsis inside, then do a braking burn to take apoapsis in as well. But that's a lot of propellant.
A lot of propellant, or you could try aero capture or aero braking, but until Cassini flew there, we had no idea how clear it would be.
Okay, thank you.
Well, that's, yeah.
Hi.
Hi.
I was wondering, do you use plutonium to power Cassini?
Yes, we do. But we use plutonium in a very interesting way because plutonium, that's P238, is very hot.
Yeah.
And so all we're doing is using the heat from its radioactive decay to power little thermoelectric cells. We have 3 of them on the spacecraft. You can look at the model later and see them at the bottom there, these black things. And so it's the heat from plutonium that gives us the electricity. And that's all we use it for. We actually use chemical rockets fuel for the propellant. And the plutonium well, as a good example, Voyager's coming up on its 40th year, and they're still going fine on plutonium. Cassini has lots of electricity, just no propellant.
Yeah, if you look at the Voyager model, that big black object off to one side, Cassini has 3 of those, and that's what contains the plutonium that the heat is used to power Voyager and to power Cassini.
Another question is, do you have an idea of what the pentagon could be made of?
Or what the hexagon at the North Pole is made of? Well, it's a jet stream, so it's made of gas, but going around very fast. That edge of the hexagon is like a giant racetrack, and the clouds just race around there faster than just about any place else. Why it has 6 sides and what keeps 6 sides on it, we have no idea.
Thank you.
Yeah, I was wondering if the ring gaps seem to be always caused by moons that clear out the debris, or maybe moons that were once there and were ejected at some point, or are they like dynamic and constantly changing?
Well, initially with the rings, we thought that the gaps had to have moons because we saw Pan in the Yankee gap, then we discovered Daphnis in the Keeler gap. But there are gaps in the C ring. Some of the gaps have ringlets inside of it, and we looked and we looked and we looked. We didn't find any moons in any of the gaps in the C ring. So there's some process that we don't understand quite yet that can keep gaps open without moons. So if you have a good idea, let us know.
Thank you.
Howdy. I actually had 2 really quick questions. One was about Pan, that odd ridge-shaped feature on its equator. Do you know like the consistency of that? Is it more of like a rocky material or more of like something equivalent to sand?
Okay, well, the rings are made 99% of water ice.
Right.
And that's also true of the moons. And we can also, through some mechanisms, figure out how porous how porous it is. An ice cube would be not porous at all. A snowball would be quite porous. Pan is much more toward a snowball than it is toward an ice cube. Okay. So there's a lot of porous space in between, and it's water ice.
Okay. My second question was in regards to the final orbit. Right now, the final orbit is is perpendicular to the rings. Was it ever considered to do a orbit more parallel to the rings? Was that ever a consideration?
Do you want to answer that?
Well,
the navigator? That's a good question. They did find something.
It's a great question.
Yeah.
But what happened, actually, when we first started with Cassini, we didn't think we could do what we've done. So the techniques, the astrodynamic techniques and the numerical techniques have been evolving. And we actually do now know, based on some work from the Cassini navigation team, that we could have these so-called ring skirting orbits. But by that time, and interestingly enough, we developed the Cassini project, the nav team developed these responses more as we ran out of propellant too early. By that time, we had invested so much time and energy and our propellant reserves in getting ourselves into these grand finale orbits that it really wasn't an option. But it's out there, and we're actually seeing maybe some mission proposals next time around to do that.
Right. When Cassini launched, we had no idea you could dive in between the rings and the planet. And that just took the evolution of software and of the right people to find that. So actually, a group at Purdue first found it. Then people here at JPL were the ones that actually came up with and finished the grand finale orbits.
So it's possible that the next Saturn mission will be more ring focused or something along those lines.
There's almost a ring hovering type mission now that the astrodynamics allow it to happen. It just need to get it started.
So just sort of answer that. The priorities, if we were to go back to Saturn, NASA has a New Frontiers program. And in it, there are 3 possible Saturn missions. One is a Saturn probe, send a probe deep into Saturn's atmosphere, measure Nobel gases and the composition as you go down. The next is Titan as a target, orbit Titan, land on Titan, float in Titans, methane seas. And the third is to go back to Enceladus. So those are the 3 major targets. New Frontiers is a much smaller budget than a big flagship like Cassini, but at least there's 3 of them, 3 possibilities. In November, they'll down select. I think they got 40-some proposals, go down to 3 to 5, and then further down select probably a year after that. So we'll see if Saturn is still in the mix, going back to Saturn. But it's still, it's probably 30 years from now until we get back. It's a long trip.
Fingers crossed.
Yeah.
Thank you.
I have a 2-parter also. First question is, how long out are you able to plan for this? Like a 30-year mission how long are you able, I mean, do you start off with a 5-year plan and then you figure that out, and then after another 5 years, you do another 5-year, like how much out do you end up before you like reevaluate?
You pretty much plan end to end. You plan, when you're going to launch, how long the cruise is going to take, and what your prime mission would be like. And that's part of the package that you put together and give to NASA for the missions that you want to fly. So when we first Cassini started in 1990. We picked the instruments, built the spacecraft. We knew it would launch. We had some launch slips and things, but when it launched in 97, we knew exactly when it would get to Saturn. And we knew exactly what those 4 years would look like.
That solstice mission that I showed you actually was planned in 2009, right down to almost the final set of orbits. Now, there are certainly some tweaks and modifications, but we really take the long view on that final set.
So I'm also curious, the crash into Saturn with Cassini, was there a plan B, and why wasn't plan B chosen?
Probably plans A through F, maybe through H. And again, it's the science.
Right, yeah, the science drove it, and more than that, the fuel light's on, it's red and it's blinking. And it's saying, you're almost out of gas. In fact, we don't use the main engines, we use the hydrazine reservoir now. And it really was the fuel. Healthy spacecraft, great instruments. We just need a way to refuel, and we'd be fine.
Thank you.
Do we understand why the Saturnian system is so complex compared with any other solar system or any other planetary system in our solar system?
Well, the Saturn system looks complex. You've got the main planet, you've got the rings and 62 moons. But the Jovian system has complexities of its own, as do the systems of Uranus and Neptune. We just haven't studied Uranus and Neptune as well as we've studied the Saturn system. Saturn just has these great, big, wonderful rings. But so do Jupiter, Uranus, and Neptune. They have rings too. They have fascinating moons, maybe not quite as many. But there's a lot of complexity with those outer planets.
In other words, it just happened.
Yeah, we don't know. That's a good question. Why the moons ended up, the order and the masses, that's a really good question.
Yeah, the same question for both of you. There have been many surprises on this mission. What was the biggest surprise for you?
I'll let you take that. What's the biggest surprise?
I guess I've still got to go back to Enceladus. I mean, there's just something absolutely magical about this. I mean, again, it's just totally out of the blue that it would be as dynamic as it is, and not only dynamic in a geological sense, but to have all the chemistry going on as well. I mean, that's rewritten the book. It's promoted itself from a class 0 to a class 3 object, and by those I mean planetary protection terms. It is something that, once in a lifetime, you're walking down the trail and you find a ruby, or it's just amazing.
Yeah, I mean, Enceladus was a complete surprise. A moon 300 miles across. We thought for certain it would be frozen solid. And to fly by and see active geysers coming out of 4 fractures at the South Pole, mostly water vapor and water ice particles, but you found organics, you found carbon dioxide, methane, ammonia, then the global ocean that was around the rocky core, hydrothermal vents on the seafloor. That hydrogen coming out has enough energy in combination with methane. In fact, a scientist did a calculation. There's enough hydrogen coming out. The energy there is the equivalent of 300 cheese pizzas per hour coming out of, out of Enceladus. If you wanted microbes, you had a lot of hungry microbes. You have a lot of food there for them to eat. So basically, I think one of Cassini's legacies will be we've changed the way we look at where you can find life. It doesn't have to be in that Goldilocks zone where the Earth is, where you can have liquid water on the surface. It could be beneath the icy crusts of worlds like Enceladus, Europa, Titan, and perhaps other worlds. So I think that's probably the biggest shift in our thinking. Where do you go to look for life? And if we found life in Enceladus's ocean, it would be remarkable to think that life could form underneath the icy crust. It would be totally a different path from the life that we took on our planet. And by the same token, if we didn't find life in Enceladus's ocean, that would be remarkable as well. Because it would show you, here you have this habitat, you have these ingredients, and yet life didn't get started. And so maybe life on the Earth is special. So either way, whatever the answer to that question, whether it's Enceladus or Europa, it will be remarkable whatever that answer.
Thank you.
Two quick questions. One, is there a contingency plan if any of these last orbits throw a wrench in the works or surprise? Sort of like not finding dust, maybe you find something you weren't expecting. And the second question is, in the sort of contingency planning, is there any thought or imagination as to what happens when you put a little bit of plutonium on a planet that probably didn't have it to begin with?
You want to take the first part? I'll take the second part.
I'm sorry, I got.
Oh, okay. The contingency plans. Once we got the final flyby of Titan, 127th flyby, we were put into what we call a ballistic trajectory. And if something happened to Cassini, the bits and pieces or whatever, or the damaged Cassini, would follow the same orbits, ending up in Saturn on September 15th. So we don't have to do anything else. And that's why NASA's planetary protection really liked this set of orbits. We could get in there, take the risk, something happens, the mission is still going to end with that. As far as putting plutonium into Saturn, if you look at the mass of Cassini compared to the mass of Saturn, it's pretty tiny. And one thing is kind of cool to think about, we're putting a little piece of Earth into Saturn. And we're going really fast, and it's going to be very hot, so if we do have any microbes there, they're going to be toast.
Thank you.
I have two more questions. One question would be, what would you do if you lost connection with Cassini?
You want to take that, Earl?
We would keep looking. Cassini, and that, I don't mean to be glib, but what happens if Cassini has a tremendous amount of what we call fall protection software built into it. So if we were to lose contact with Cassini, we have to talk to Cassini and Cassini has to talk to us. If, for example, we lost contact and Cassini didn't hear from us, it would start looking for the Earth. And meanwhile, we're starting to look for Cassini. So we go through days and days and potentially weeks of allowing Cassini to turn on different hardware, different radios, point its antenna different ways. Meanwhile, we're using all the antennas all over the Earth to try to recommand it. So if indeed it happened because Cassini failed in some way, then we, of course, wouldn't hear back. But it would be a long time before we gave up.
We probably wouldn't give up till the end.
My second question is, are you going to start another mission after Cassini ends?
Well, there's another mission in the works to Europa. It's called the Europa Clipper. And so NASA has selected to go back to this other ocean world and to study it and learn more about it for possible future missions. There's even a proposal for a Europa lander to find a place where there might be plumes on Europa, put a lander down on the surface, and sample and look for life coming from that plume. So that's sort of next on the books. I hope there's a lot more. I want to go back to Uranus and Neptune and back to Saturn and Enceladus. So hopefully there's a lot more.
Thank you.
You want to read some of the questions?
Let's give
okay.
Thank you. Following the goodbye kiss, will you have control over the angle of descent into Saturn's atmosphere? You're saying no, you won't really know the angle?
Well, we will know this one thing. Till the very last second, we'll be pointed the high gain antenna at the Earth. And that's our goal. And then while we do that, the other axis is pointing the ion and neutral mass spectrometer in the direction of Saturn's atmosphere. So we have picked that orientation. Send back the most data the longest possible time.
The spacecraft will be controlling its attitude until it can't. And
I see.
so we will know and it will not only be controlling it, it'll be telling us what it is, again, until it can't.
Would the hope be that it goes in maybe a little more shallow than steep, just to give you a few more seconds?
No, it's going in.
It's going in.
It's not going to skip out. It's not going to skip out.
If it comes out, we're going to be both very embarrassed and having to deal with a very damaged spacecraft.
Thank you.
I'm not quite sure how to ask this question, but
great shirt, by the way.
Oh,
Yeah,
thanks.
absolutely. Thumbs up on the shirt.
How do I say this? So there's a lot of talk about the science, but what I'm curious to know is that this is technology that we had 20 years ago, right? When it launched, and so now it's 2017, and so and it feels like Cassini, the analogy that I think of is like a jazz musician. It feels like you're just kind of riffing, and you're kind of just going around and not necessarily making it up, but you have like a hunch and you kind of go for it. Knowing what we know now, you know, like what will we bring to the next jam session, I guess, you know, like what technology has evolved, or what have we learned, or what kind of technology do we wish we had on Cassini that we'll have for Europa Clipper, I suppose. And it's more
Right. Certainly, had we known the potential for life in Enceladus's ocean, if we knew it had an ocean, we would have carried more capable mass spectrometers. That we have mass spectrometers can only look at like 100 atomic mass units, 100 protons worth of molecular size. That's not nearly enough to look for fatty acids, amino acids, evidence for life. So you would carry mass spectrometers, instruments that could do the sampling, that could help answer you're getting free samples, so take advantage, you know, and check it out. And who knows with the camera technologies, you know, our cameras may not be as good as the cell phone cameras of today. So you could do a lot more with the cameras, the spectrometers, all kinds of instruments with the technologies today. And we'd have a lot of more orbit choice too. We could do skim across the rings, finding this unique orbit, maybe go inside and come back out. Now that we know it's clear, you know, we could do maybe a lot of things differently. Carry 2 probes, maybe a Titan orbiter, you know, lots you could do.
Okay, great. Well, thank you so much.
You want to, okay. After this, we're going to ask a couple questions from online.
Okay.
Yeah.
One of the objectives that you named for this final dive is to keep Titan pristine, but Huygens has already gone into Titan. So was there special protection done, or was it done on the assumption that we weren't going to find as much as we did there?
No, I think that's a fair comment, and we really have to be very careful about Titan's classification. It still is and was what we call a Category 2, which means that the probability of contamination influencing future investigations is very, very low. But nonetheless, you know, Huygens soft landed, and you're absolutely right. It wasn't cleaned any more than Cassini was. It wasn't decontaminated. And so it could have potentially left microbes on the surface. But again, we're bringing plutonium, lots of it, onto the surface, potentially. And again, it's something that we would need to take every reasonable precaution to avoid. But Enceladus went from Category 1 or even maybe 0 to Category 3, which means that the probability of our requirements on the probability of inadvertently striking it are much more stringent. And that's really the driver. Titan, at the time, it seemed fine, and you know, you can't undo what we did, and the classification hasn't changed, but it still looks different now than it did.
Right, you could still land on Titan, the way it's categorized now. And in part, the icy crust is so thick above the ocean of Titan, which is where we'd worry about Earth kinds of life, that is, you know, so that's why it stayed a Category 2. And there's no direct contact. We don't see any geysers or, you know, jets or anything coming out from Titan's surface.
Okay, thank you.
We've got a few questions from the internet. Ocean McIntyre, and this is for you, Linda. Are there any suspected reasons for the lack, in fact, they're all for you, any suspected reasons for the lack of dust within the ring gap?
Wow, that's a great question. Why no dust? That's a really good question. We don't know. We're hoping with a few more orbits we can, in a little bit more time, figure that out. But complete surprise. Of all the things we would have guessed, no dust was not even on the list. So.
And then the dynamics for polar activity or inactivity look impressive. Can you elaborate?
Okay, for polar activity.
Air Plants Decor asked that, yeah, about polar activity.
Okay, I think it was probably talking about the hexagon and the vortices, the hurricane-like vortices at the poles. You know, Saturn is spinning, it's mostly gas. We know hurricanes on Earth tend to migrate, you know, toward the poles. They don't ever make it there because they're out of energy. But we have those two hurricane-like features right at the poles. And the energy source for the hexagon for that jet stream, that's a really good question. We're hoping our pictures and new data will help us figure that out.
I think that must be the inactivity references to the stability of that hexagon.
Right. It's been there at least 30 years. Voyager discovered it.
And then here's a good fitting question. AJ asks, will there be a follow-up mission to Saturn in the future?
Oh, I certainly hope so. Saturn to Enceladus, Saturn, Titan. There's so much we've left, so many questions that we now have open for a future mission. So thank you very much. Thank you for coming.